Hi, we are on Chapter 11, A Revolution in Names. This revolution needed a new system of names, though Lavoisier thought Lavoisier names which reflected the elements of which things are actually made of. Calx of mercury is really mercury that has taken on oxygen, and so it should be called mercuric oxide. That is how we still name chemical compounds today. If you read a textbook of chemistry written prior to the publication of Lavoisier's elementary treatise on chemistry, it would make no sense because it would use such names as had been used all the way back to the days of alchemy: powder of algaroth, turbeth mineral, calcalarth, phagedenic water, pomphylics, glauber salt, oil of vitriol, butter of arsenic, sugar of lead, and liver of sulfur. But a modern chemist student who picks up Lavoisier's Elements treatise on chemistry will feel right at home, for it is the home which Lavoisier himself designed, and almost all of the names of the chemical elements and compounds would be familiar. You would not find 109 elements, however, but only 33. Most of these 33 would be the elements on our own chart today, but some are no longer counted as elements. You would find 6 nonmetals: sulfur, phosphorus, charcoal, muriate radical, fluoric radical, and boric radical. But only sulfur and phosphorus remain on our element chart today, although one might consider charcoal to be close enough to carbon. And you would find 17 metals: antimony, arsenic, bismuth, cobalt, copper, gold, iron, lead, magnesium, mercury, molybdenum, nickel, platinum, silver, tin, tungsten, and zinc. All of these will still be found on our own periodic table of elements. You would find 5 of what he called simple earths: lime, magnesia, Bartes, alumina, and silica. You will not find any of these on the periodic table, however, because they are not simple at all. Lavoisier was wrong. They are not elements but compounds. The real elements, aluminum and silicon, were not isolated and properly identified. Until the first quarter of the 19th century. Lime is a compound of calcium and oxygen. Magnesia is a compound of magnesium, carbon, and oxygen. Bartes is composed of the most part of barium, sulfur, and oxygen. And finally, you would find the following 5 elements: light, caloric, oxygen, azote, and hydrogen. 3 of the 5 will be found today, with azote's renaming as nitrogen. Light and caloric. Lavoisier thought that light and caloric, that is, heat, were elements. Fortunately, this error did not disturb the soundness of the foundation of chemistry he was building. But Lavoisier gave us a way to fix even his own mistakes by establishing a proper definition of what an element is. An element is the last point which chemical analysis is capable of reaching. If it cannot be taken apart by any further chemical analysis, it is an element. If it can, it is not an element but a chemical compound. Water is not an element, but oxygen and hydrogen are. The definition allowed Lavoisier to do away with the old list of 4 elements: earth, water, air, and fire, and built a new list consisting of those substances which he thought could not be broken down any further. But he thought scientists had to keep testing the item on the list and keep looking for new elements, and they did. As we've seen, some of the elements Lavoisier listed were actually compounds. Many of the new elements were added, and finally some, like light and caloric, were found not to be either elements or compounds. There is one last thing we must notice about Lavoisier's list of elements. They are not yet put in the place that we find them on the periodic table. They are just in a list. The elements could not be shuffled around into the right places until other revolutionaries completed what Lavoisier had begun. Who knows, Lavoisier might have done it himself, but another revolution, the French Revolution, cut his days short. Although Lavoisier had done many things to help both the rich and the poor in France, before and after 1789, the political revolutionaries believed that anyone who had helped the king at all was an enemy of the people, even if it had helped the people too. On the 24th of November he was arrested in his laboratory in the midst of an experiment. He was tried by the Revolutionary Court, and his guilt was quickly established. The charges: Mr. Lavoisier was guilty of adding water to tobacco, of building a wall around Paris to the detriment of the people's health, and of collecting excess taxes. All of these charges being merely trumped up so that Lavoisier could be executed by his enemies. On May 8, 1794, Lavoisier walked up the steps to the guillotine. The great French mathematician Joseph Louis Lagrange sadly remarked, "It required only a moment to sever his head, and probably 100 years will not suffice to produce another like it." Chapter 12. Nature never creates other than balances in hand. It may have looked like Lavoisier that all the hard work of chemists had been done. While Lavoisier certainly set things going in the right direction, there is still much to be discovered on the way to the periodic table. Nature seems always to have more surprises, and the more we look into its order, the more order we find. But now we have to move from the visible to the invisible world, from the macroscopic to the microscopic. We must move, in short, to the atomic world, for it is there that we shall find the logic of the periodic table's delightful order. Now, it is true that Lavoisier gave chemistry a very sound, if humble, definition of an element, the last point which analysis is capable of reaching. But what happens, we might wonder, when we dig more deeply down beyond the level of visible elements like silver, gold, and sulfur? Are each of these made of smaller pieces of silver, gold, and sulfur, or something else? That is just the kind of question chemists were asking each other around the beginning of the 19th century, just after the time of Lavoisier. And to answer it, chemists had to reach back to Boyle and his atoms. But this did not happen all at once. Chemists were very cautious folks. They did not go in for airy speculation about things they could not see. They wanted solid reasons based on the evidence of what was right before their eyes in the laboratory. We might begin with the German chemist Jeremias Richter. As with many of the greatest of discoveries, Richter's contribution to science was the result not of doing anything new, but of looking more carefully at what had already been done. Chemists, and indeed alchemists, had been working with acids and bases for a long, long time, centuries. They knew that bases neutralized acids, and acids neutralized bases. You must probably realize the same thing when you were pouring baking soda, the base, into the vinegar, the acid. You kept pouring in baking soda until it would not fizz anymore. At the point just where it stops fizzing, the solution was neutralized, unless you poured too much baking soda in which case you made the solution a base. If you had thought to test it with the purple cabbage juice, you would find that the juice stayed purple, and that it was a sign that it was neither an acid any longer, or that it turns the juice red, nor had it yet gone over to become a base, thereby turning the juice green. This solution between the acid and the base chemist at the time called a salt, but today we say that it has a pH of 7 on a scale that runs from 0, strongest acid, to 14, strongest bases. You may then have wondered how much of a base it takes to neutralize a certain amount of acid. If you did, you would want to know the same thing in regard to other acids and other bases. Then congratulations, you were thinking just like Richter. Richter asked himself, if it takes 1,000 parts of sulfuric acid, a part just means any amount you happen to choose, whether a gallon or a teaspoon. How much of each base that I know will it take to neutralize it? Fairly soon, after a lot of careful measurements, he drew up a table of comparison. A man named Ernest Fisher recognized Richter's table in a clear way, so we all use his, and even though only some of the table. Okay, here is his table. How does Richter's table work? Quite ingeniously. If you want to neutralize 1,000 parts of sulfuric acid, you would simply use 615 parts of magnesia, or 672 parts of ammonia, or 859 parts of soda, or 1,605 parts of potash. And what if you were out of sulfuric acid? Well, you could just substitute 1,405 parts of nitric acid. Low on nitric acid, use 979 parts of phosphoric acid instead, and so on with all the other acids and bases. The table, called the table of equivalents, because it gave the equivalent amount of bases and acids for achieving neutralization. All very interesting, but what does it have to do with getting us to the invisible world of atoms? Isn't it odd that the relationships are so regular that wherever you are, anywhere in the world, exactly 859 parts of soda will neutralize 1,583 parts of citric acid? It suggests that all these chemical compounds, both acids and bases, are very precisely formulated. Chemical compounds, that is to say, are not like vegetable soup. You do not find that you get vegetable soup only if you combine exactly 49 parts of carrots and 87 parts of potatoes and 100 parts of water. Vegetable soup has a recipe rather than a formula. You take a few cups of water, put in some carrots, some potatoes, a sprig of parsley, a handful of peas, a pinch or two of your favorite spices. A recipe is a matter of more or less, but a formula is very exact. There is another sign of exactness on Richter's chart. We only find whole numbers, not just a little over, not 615 and parts of magnesia, but 615 parts on the button. Very strange. Things are so neat and precise that it looked like a conspiracy of order. But even more interesting, things were soon discovered. For those, we turn to the controversy between two French chemists, Cudel Berthollet and Joseph Proust. Both Berthollet and Proust and many other chemists besides recognized that they could make different compounds using different amounts of the very same element. For example, they both knew that two elements, carbon and oxygen, can make two different compounds, one called carbonic oxide and the other called carbonic acid. Now, Berthollet thought that the elements of the compound could come together in variable and indefinite ways. To continue our example, if Berthollet was right, you could keep adding just a little bit more oxygen to carbon and make a whole continuous line of compounds between carbonic oxide and carbonic acid, like going from black to white through various shades of gray. But Proust thought that the exact opposite. He argued that each compound had a definite formula, so the elements combined only in very definite and invariable ways. Using our example again, if Proust was right, there were no compounds in between carbonic acid and carbonic oxide and carbonic acid. No grays, just black and white, as to speak. Proust won the argument, not by words, but by repeating experiments. If we use the names of the compounds we use today, we say that the chemistry has followed Proust. Carbon dioxide, carbonic acid, is contained exactly twice as much oxygen by weight as carbon monoxide, carbonic oxide. The prefix di means two and mono means one, and there are no compounds in between. This is called the law of definite proportions, or sometimes it's called the law of constant composition. In its precise form, the law stated, in a compound the constituent elements are always present in a definite proportion by weight. This means that compounds are not a recipe such as we use for soup, but very precise formula such as we use in mathematics. We find exactly 2 times as much oxygen by weight, not as little or over under. The amount by weight of each element in different chemical compounds always change by a whole number, 2 times as much, 3 times as much, or even 4 times as much. This becomes clearer if we look at a list of compounds made from 2 elements in modern symbols, along with their modern names. The numbers here do not, we should mention, symbolize weight except for quite indirectly, but is directly enough for our purposes. So methane 1 carbon, 4 hydrogens. Ethane, 2 carbons, 4 hydrogens. Propane is 3 carbons, 6 hydrogen. Propane is 3 carbons and 8 hydrogen atoms. But we must note that chemists at the time did not speak of 1 carbon atom or 8 hydrogen atoms, nor did they know symbols as CH4 or C3H8. They only knew that the weight of each element was double or triple or quadruple. We shall soon see John Dalton and John Berzelius to find such atoms and symbols, but Press did not know that elements are not just thrown together in the old way to make chemical compounds. As he declared, we must recognize an invisible hand which holds the balance in the formations of compounds. A compound is a substance to which nature assigns fixed ratios. That is, to use again our modern notation, the ratio of carbon to oxygen in CO is 1 to 1. Then the ratio of carbon to oxygen is CO2 is 1 to 2. For Proust, then a compound was something which nature never created other than balance in hand. Nature works by formula. Chefs work by recipes. It is as if the designer of nature was something of a mathematician rather than a cook. Very strange and very wonderful. Now we have better get going to the atomic world, where things are even more strange and even more wonderful. All right, see you again tomorrow. Bye.